9.4 is a hyperbola. It is the last conic section we're going to deal with, this one here. It has two pieces to it, one at the top and one at the bottom. You've probably seen hyperbolas graphed before. If you graph the reciprocal function y equals 1 over x, these hyperbolas look like this. And they have asymptotes that are horizontal and vertical. And they can move around based on the equation. If it's just 1 over x, then the asymptotes are the x and y axis. This is the same as having x times y equals 1 if you multiply both sides by x. So it's called a reciprocal function because, like, if x times y has to equal 1, then whatever x is, y is its reciprocal. 4 times a quarter equals 1, or negative 2/3 times negative 3/2 equals 1. They're just reciprocals. The conics that we're going to graph aren't going to have this orientation, but they're going to be pointing up and down as a conic. That's one single hyperbola. Or they'll be pointing side to side with a horizontal orientation as the other. So here is the equations for hyperbolas, and here's an example of one with a horizontal orientation. Again, we just have our a, b's, and c's like we always do. The ones that we're going to be doing in this class are going to be centered at the origin, so there's not going to be any h or k term. H and k are just 0, really. We're just going to be messing with a, b, and c. Now, hyperbolas and ellipses have this simple difference in their equations. With ellipses, these would be pluses and not minuses. But because we're doing hyperbolas, they have a minus there in the equation. What we're looking for is which variable comes first. If the y variable comes first, it's going to have a vertical orientation. If the x variable comes first, it's going to have a horizontal orientation. It doesn't really matter which is a and which is b. Like we put them there. With hyperbolas, we always put the a value underneath x and the b value underneath y, just so that this stuff works out simply every time. But all you have to think about is, again, these are just distances. The b value tells you how far to move up and down. The a value tells you how far to move left and right. We're going to work with center, vertices, co-vertices, which for this graph would be up here-ish somewhere, foci, and asymptotes. These are asymptotes that the graph approaches, and I'll show you how to work with those. The other simple difference is hyperbolas use the good Pythagorean theorem, not the evil one, just the regular one. A squared plus b squared equals c squared. Okay, so we're going to graph this hyperbola here. Since the y variable is coming first, it's going to have a vertical orientation. So I'm going to say that my a value is root 11, which is about 3.3, and my b value is 5. The center of this hyperbola is going to be at 0, 0. And this just means from the center, if I move left and right 3.3, these right here are my co-vertices. The co-vertices aren't actually on the graph. They're going to be used to help create the graph, but if you plugged in 3.3 for x and 0 for y, you would not get out 1, you would get out negative 1. I mean, 3.3 squared gets you 11. 11 over 11 is 1. But then there's that minus hidden in there, and the minus subtracts them, so you'd get a negative 1 when you plug in 0 for y. So the co-vertex isn't actually on the graph. It doesn't fit in the equation, but it's still going to be used to make the graph. The vertices are up and down 5. So there's a vertex here and a vertex here. That will actually be on the graph itself. Now, something pretty simple and interesting happens here. I'm going to create a box that contains the vertices and the co-vertices. I could do this with my box drawing tool if I wanted to, but I want you to kind of get a feel of how this has to be, how this looks. The co-vertices and vertices are contained in this box. So really this point right here is the point 3.3, comma 5. That's what matters. The corners of the box are important because through the corners of the box, I'm going to graph asymptotes. There's going to be an asymptote here and an asymptote here. And this graph that I'm drawing, this graph that I'm creating, is going to use those asymptotes. So I'm going to stretch them out a little bit. Use the asymptotes and curve towards them the whole time. I'm going to see if I can actually grab this whole thing and slide it down a little bit. There we go. That's a good looking graph. All right, so I haven't graphed the hyperbola yet at all. I still need to, make that happen. The hyperbola itself is going to come through this vertex and slide out towards these asymptotes. So there's one half of the hyperbola, there's the other. The yellow curve there is the hyperbola itself. Every point on that function, every point on that graph, I could plug into this equation and get out a true statement. The covertices are just used to make the box. The foci is the last thing we're going to be having to plot here. The foci are always somewhere inside the curve. All foci are always inside the curve. That's true for circles, ellipses, hyperbolas, and parabolas. So I have to find the foci. To find the foci, I do a squared plus b squared equals c squared. And c is my distance to travel to get to the foci. So that's 25 plus 11. Technically it's 11 plus 25. I mean, this is where it doesn't really matter. But technically the a squared is 11 and the b squared is 25. So 36 is c squared. So 6 is c. So there's going to be a focus here and a focus here. Now that's everything I needed to find. So I now know that I have a vertex at plus or minus 0, 5. Sorry, 0 plus or minus 5. I have a covertex at plus or minus 4, 0. I have a the foci are at plus or minus, or 0 plus or minus 6. And then the asymptotes are really quite simple. This is a line, and this line is traveling through the origin, so its y-intercept is 0. And I already know its slope. It's going up 5 and right 3.3. It just comes from these numbers here. So the asymptotes are going to be at y equals plus or minus 5 over 3.3 x. It's just slope-intercept form with a y-intercept of 0. Now, we don't really like 5 over 3.3. That looks awful. I can remember that 3.3 actually came from root 11. And then we can't have a root 11 on the bottom, so I rationalize, multiply the top and the bottom by root 11. So we get plus or minus 5 root 11 over 11 times x. That is the asymptote. The domain of this function is all real numbers. I could plug in anything for x, and I'll get out 2 things for y. I've got to stop calling it a function. It's not a function because there's 2 outputs for 1 input. The domain of this equation is all real numbers. The range is everything except for negative 5 to 5. So the domain is all real numbers. The range goes from negative infinity to negative 5, and then from 5 to infinity. Now, just so you know, if the x values and y values were switched, so if the equation was x squared over 11 minus y squared over 25 equals 1, the box would be the exact same. The asymptotes would be the exact same. The vertices and covertices would just switch their spots. This graph would just look like this. So what was a covertex is now a vertex. What was a vertex is now a covertex. And the foci would still be at 6, but it'd be 6 left and right, not 6 up and down. So that would be a different looking hyperbola if the x values came first and not the y values. That's what happened here. Here we have the opposite, problem. We're given a graph. From the graph, we have to write the equation. So this graph has a horizontal orientation with vertices at plus or minus 3, 0. So because it has a horizontal orientation, I know it's going to be x squared over a squared minus y squared over b squared equals 1. I just have to find a and b. Well, the a value is 3. The b value is 4. So I can write the equation really simply. X squared over 9 minus y squared over 16 equals 1, and boom, we've done it. If I want to find the foci, that'd be at a squared plus b squared equals c squared. So c is clearly 5. So there's going to be a focus here and a focus here. And the asymptotes are going up 4, right 3. So the asymptotes are y equals plus or minus 4 over 3x. Something else I want to show you that's pretty cool about hyperbolas and ellipses. Like I said, the only difference in the equation is that this minus for an ellipse is a plus It's a minus in a hyperbola and a plus in an ellipse. If I were to take this equation and actually change it and give it this plus right here, I could still use this same box. The vertices and co-vertices don't change, and the ellipse would fit right inside this box. In fact, when I use the ellipse tool on this program, I come up here and tap the ellipse, I actually just click and drag from one corner of the box to the other corner of the box, and that's how I make the ellipse. So the ellipse fits inside of the box that also gives the asymptotes of the hyperbola. So ellipses and hyperbolas are sort of like inverses of each other. They're not quite. That's not an exact term, but you can sort of think of them as a type of inverse or a type of opposite. Let me show this on Sketchpad. Here is an ellipse with a center here, a center right here, and two foci here. As the foci get closer and closer together, the ellipse gets more and more circular. So when the two foci are on top of each other, it actually is a circle. So a circle is an ellipse. It's just an ellipse that's very specific, kind of like how a square is a rectangle. As I pull the foci farther and farther apart, the ellipse gets tighter and tighter and tighter and longer and skinnier, and eventually it's going to break through and form a hyperbola. So it's like here the foci is just too far apart to make an ellipse, so it makes a hyperbola. Here it's so close together we get our ellipse, and this right here is a circle. So they're all kind of related to each other, ellipses, circles, and hyperbolas. Hyperbolas have a center, vertices, co-vertices, and foci, just like ellipses. You can find their asymptotes with the equation y equals plus or minus b over a times x. Hyperbolas have symmetry through horizontal and vertical lines, as do ellipses. So, like in this case, the x and the y-axis are both lines of symmetry. And they use the good regular Pythagorean theorem to find the value of c, a squared plus b squared equals c squared. Have I told you that you look nice today? Because you're doing a good job. Again, keep keeping it up. We did it. We got through another math video. Thanks for watching. Here I'm going to play with the perspective on these shapes while I talk to you. Please subscribe to the videos, like the videos. Okay, start this thing over. You did it. You got through the video. Thanks for watching. I'm going to play with the perspective of these shapes, which is always pointing towards that center while I talk to you about things. Please subscribe to the video, the channel really. Please like it if you found it helpful. If you want to share it with friends and say, hey, this guy's not the worst, that's an option too. You can always take your video quiz if you're in my class. And comment down below. See you next time.